I still know how to do all this. Are you
And
the
you don't.
technic? I was going to wonder if the technical gremlins all worked out.
I still have one monitor that is displaying everything rotated at a right angle.
And I see your face being sort of delayed in strange ways. So, so I think we've got enough of the technical gremlins worked out that we can proceed with the recording, and we'll see how we go from there. Well, hey Pamela, it's good to
Yeah.
see you again.
It's good to see you. How are you doing?
Good. Did you have a good summer?
I had a long summer.
Yeah, we had a really great warm summer. We swam in all the places and jumped off all the things into the water, and that was literally all we did every day. We just went swimming,
Oh,
jumped off
well,
things, rinse, repeat. Sometimes twice or three times in a day. It was great. Yeah. But you,
I
but
jumped off nothing into water.
well, it's not as fun, I think, to jump into lakes and oceans. But you had a really cool trip. You did a trip to New Zealand.
Yes, that doesn't count as summer anymore.
It's
That
it's
was
winter.
recently. It's definitely fall, and getting down there, it was definitely the end of their winter, going into spring. All the tulips were in bloom. Yeah, I went down and went to Wellington, Melbourne, and Sydney, and gave about two talks a day for a week, and it was an insane whirlwind trip. And Wellington has the most amazing geology and biology because it's an island that's very, very, very young and not yet tamed. So that
That's
was kind
great.
of cool.
Wow, I'd love to get there sometime. Um, in fact, we had an astronomer last night in the virtual star party from New Zealand. I don't know if you met him, Astro Stu, Paul Stewart, and he was broadcasting the sun live into the star party while we were doing the night stuff, and it was just the most amazing video, just unbelievable.
Yeah. Yeah, New Zealand is two different islands, and they refer to Australia as the West Island. And I was up on the North Island, and Paul lives down on the South Island.
Okay, so if people have never done this before, if you just want a reminder, what we're going to do is we're going to record our episode of Astronomy Cast live. So we're going to you get to watch as this stuff just tumbles out of our brains, especially Pamela's mighty intellect. I'll ask a bunch of questions, she'll answer them, and that will be our episode. And today we're going to do a show on particle accelerators, which is great. I'm really excited about this. Pamela's like, oh, why don't we do particle accelerators? And I'm like, yeah, let's totally do that. Some episodes I'm super excited about, and this is one of them.
Well, there's a lot of misinformation about particle accelerators, so it seemed like a good thing to do.
Like what they are. It's
Well, yeah, there's
is the
that.
start. The other thing is right, and so then now you can interact with us. So we're going to record the show. It takes us about 30 minutes, and this is the show that normally goes out into the podcast feed and people consume. But we actually stick around for another 20 minutes, half hour after that, and just answer your questions about space and astronomy. So there's two safe places that you can ask your questions now, and unfortunately, the technology that we use to keep track of all of the information is not as available to us anymore.
Yeah.
So the two places to look, the two places that I'm going to monitor are on the event page. So if you're watching that on Google Plus, there's an event page, and if you're watching it there, I will be able to catch your question. I can see Graham is making comments, Paul Steele, Kevin Parker. So that's the place that you can make some questions. The other place is over on YouTube, and I'll keep track of the comments on YouTube as well. So if you're watching it anywhere else, literally, if you're watching it embedded on Universe Today or over on CosmoQuest or anywhere, you're going to want to click to watch it on YouTube or find the event page on Astronomy Cast's Google Plus page. Those are the two places. I can't guarantee I will see any other questions or comments. So, yeah. So and feel free as we record the show to jump in and fix our mistakes, and I will try to catch them and we'll incorporate them into the show. Or if you have just questions that have nothing to do with what we talk about today, we're glad to deal with those after the show. And you can experience the vast, sweeping intellect of Dr. Pamela Gay.
I can't hear you say that without giggling. I
The
just
vast, sweeping, mind-bending intellect of Dr. Pamela Gay. All right. Okay, now let's get set this up to record. You ready?
Yeah. Hold on. This is where I have to like figure out how to move my mouse on the screen that's rotated. Ah.
So your your monitor is rotated, right? So you're actually that is some technology
Stop
fail.
laughing at me.
That's awesome. That is a new form of technological fail. I've never had it's stuck on, like, you just turn your monitor sideways, prop it up, hold it out sideways.
Pretty much. Stop.
Make sure it's on mono.
Yeah, it is. It is. I'll be back to normal in a moment. Okay, I'm ready to press record at any moment.
Is it on mono?
Yes.
Cool. All right. And now I'm not pretty. Hold on. Sorry. We always explain that this is the sausage factory thing. Okay, cool. And I can see the people over on YouTube as well. Okay, good. I'm ready to go. Let's rock it.
Okay.
I'm pressing record.
I pressed record.
Testing.
It's recording.
I don't see this is not good. Hold on. Let me try again.
Do I have to
Testing.
figure out how to stop it?
Okay, good. I got the waveforms. Good. I just didn't see any waveforms, so now I'm seeing them. So, are you good?
Yeah.
Just keep rolling? Okay, here we go.
Yeah.
We'll let Preston figure this out.
We're sorry, Preston.
It's not fun for him unless we throw a bunch of curveballs his way. All right. Okay, here it goes. Astronomy Cast, episode 315, Particle Accelerators. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. It's been, for those of you listening on the podcast feed, it's been a few months since we've been recording, but now we're back to our fall schedule. You're teaching people in the classrooms.
It hasn't been a few months. It's been a month and a half.
Yeah. And now we're back to our fall schedule.
Yes.
And you've been teaching people you're teaching people in the class and teaching people through the podcastings.
Something like that.
Something like that. So good. Well, did you have a good summer?
Yeah. I went all the places.
Yeah, I know. You were in Europe. You were in New Zealand. I feel like I didn't go. Oh, I went to the Penny Arcade Expo, and that's it. You went to Dragon Con.
I went to Dragon Con.
Did you extract any audio from Dragon Con?
No, it turned out that Astronomy Cast got left off of the feeds and off of the schedule, and yeah, it just devolved.
Oh, well.
The other one I could have recorded, we'd already done, so it is what it is.
It is. Usually you like to come back with some audio, but not this year. But maybe next year. Okay, yeah. Cool. So let's get rolling. So who knew that destruction could be so informative? Only by smashing particles together with more and more energy can we truly tease out the fundamental forces of nature. Join us to discover the different kinds of particle accelerators, both natural and artificial, and what questions they can help us answer. So particle accelerators. So I think we had this conversation a few years ago, actually, and you blew my mind that I actually had no understanding of how a particle accelerator worked. And typically, I know a lot about the stuff that we talk about, but this was one that you were like, here's how they work, and I was like, what? No. So can you kind of get like that part where I think is just amazing? It's the core purpose of a particle accelerator, the whole mass, energy, mass thing. So what are they?
So this is where I think everyone gets confused. Is they're like, how is it that we're just smashing together protons and we're getting this really heavy thing out? Well, what's happening is you use a magnetic field in one form or another to take either one or two particles and get them accelerating so that they're moving as fast as you can get them moving before relativity starts to get in the way. And it's the combination of their kinetic energy and their mass coming together and all of it becoming pure energy during the collision, that leads to the discovery of things like the top quark, like the Higgs boson. Um, but the awesome thing is that's not the only type of particle accelerator out there. That's just the sexy kind that we hear about in the news. There's particle accelerators that are used to create ion beams, to burn out tumors in human bodies, to create neutron sources that we can use to make heavy radioactive materials. So there's all sorts of different types of accelerators. There's hundreds and hundreds of them on the planet Earth, and the only one anyone ever knows about is CERN when it's active, or Fermilab when it's active, and they seem to take turns.
But yeah, there are particle accelerators in hospitals and stuff.
Yes.
Yeah. So, but I think I want to go back because I think you didn't quite get there. I mean, this concept that light, that energy and matter are interchangeable, and that by dumping energy into these particles as you fire them around, you create heavy elements out when the collisions happen. Like, what's going on there?
So there's two different things that you're combining. First of all, the particle has E equals mc squared worth of energy. This is its rest energy. So you're taking its mass, you're multiplying it by the speed of light squared. So that's a pretty good chunk of energy right there. Now you're then taking that exact same particle and multiplying its mass times 1/2, because it's kinetic energy, times v squared in a non-relativistic scenario, and then that v squared gets even more complicated as you get closer and closer to the speed of light. And all of that energy gets combined, essentially in some cases almost doubling the mass of the particles not the mass, the energy of the particles that are colliding, and that becomes vast, and all of that energy is then in a very, very small point, and it has the option to freeze back out as matter in a variety of different ways, and it usually cascades through multiple different particles as it settles back down to, well, whatever it's going to be on the other side of the collision.
So if you collide these particles together in these accelerators, they have all this energy and the mass, and you always hear you could use a sugar cube's worth of matter would act like a nuclear bomb if you could release all that energy, right? But
but we're not creating sugar cubes.
No, I understand that. No, but we're taking individual protons and individual electrons and things like that, but we're smashing them together, and you've got all that energy, and then in that moment, you suddenly have a soup of an enormous amount of energy that can now freeze out into particles.
Yeah. And what's awesome is the stuff that we hear about most in the news is when people are accelerating protons or electrons, typically towards targets. And when I say accelerating, what I mean is charged particles, when they're exposed to a magnetic field, will move purposely through the magnetic field. And if you have a nice cone of wires, that will generate a magnetic field through the center of that coil of wires, and you can take and shoot charged particles down that coil of wires. Now, a charged particle isn't just an electron, isn't just a proton. You can actually take an atom, strip off its electrons, and it becomes an ion. Now you have a charged atom, basically, an ion that you can accelerate through this magnetic field. So now you have a significantly heavier mass object than just that one electron, that one proton that you're accelerating through the collider. So now you're looking to get even higher energy experiments. It gets quite messy and awesome quite quickly.
Right, and I guess so why do we need such, there's the different kinds of particle accelerators and the different sizes of them. The one we hear a lot about is that it took a facility as big as the Large Hadron Collider to discover the Higgs boson. So, why was that so necessary?
Well, you're looking at a couple of different factors when you're building huge accelerators. First of all is how easy is it to maintain the containment? So when you're accelerating the particles, you typically are creating a big circular device. There are linear accelerators, but the bulk of the ones that people are familiar with that are used in hospitals in many research settings are circular ones. So you have a giant torus, a giant donut that you're accelerating particles through. And you have two factors. You have to keep the beam contained in the center of this donut that you've sucked all the air out of so that they're not going to accidentally hit a molecule of air. So you need to consider how easy is it to suck all the air out of that. Luckily, vacuum isn't as big a deal anymore. The second thing you need to consider is how do you keep that precise bend so that they don't accidentally hit the sides of the container? And how do you build the machinery to provide the acceleration? So now you're wrapping that tube in very finely made magnets of different types. And then you're bending the beam. Now, anyone who's driven a car knows that it's easier to do a nice, big, gradual turn than it is to do sharp, little, tiny turns. And this is also true in cyclotrons. If you're trying to keep a nice, constantly accelerating beam going, that nice big circle is going to be much easier to keep things contained in, especially as you're approaching the speed of light.
Right, and so because some of your energy is going to be going to just keeping it going around that curve.
That's why it's called constant acceleration. Velocity is your motion in a given direction. The second you start changing something's velocity, that takes energy. That requires that acceleration to be taking place. So you're upping both the velocity of the particle, instantaneous velocity. You're increasing its speed constantly. But you're also constantly having to steer. So these nice giant circles allow you to have that constant acceleration and to not have as hard a time building the giant machinery that you need and keeping everything tightly focused as you go faster and faster and faster and faster.
And how many times, do you know how many times these particles are going around these accelerators? I mean, are they just doing one loop and then they're smashing?
No, they're doing many different loops. Exact number is going to vary with how fast you need them to go, how focused you need the beam, how many particles you're injecting into the beam. It's not just once. It takes many times around to get all the way up to the kinetic energy that's necessary for the explosions that they have at the end.
Yeah, it's kind of amazing, you know, that they are able to, as you say, dump in almost to the point that it has double the energy, because that original E equals mc squared is such a vast number that to get more of that energy into it.
And you can even start to get more than that except then you have to switch to using the relativistic equations. Because as you go faster and faster and faster, your momentum increases, your effective mass increases as you're going faster from relativistic terms, and your kinetic energy has relativistic terms. So now you have that vast velocity, and it seems like you have significantly more mass. So now you're exceeding, but you need a new equation, that factor of 2. It's kind of awesome.
Yeah, totally. Right. So then, what are the different kinds of particle accelerators? You mentioned linear, the circular ones. So what different flavors do they take?
Well, you can look at the flavors both in terms of technology and in terms of what they do. So if you look in terms of what they do, you have medical cyclotrons that are used to blast out tumors. You have neutron beams that are used often to fire at heavier atoms at a very precise rate to build these heavier and heavier atoms. This is how we end up discovering heavier atoms periodically, and they end up announcing that they've now found unobtainium. That one is the one they've actually found. But,
right.
But
I see.
You know what I mean.
Yeah, so they've got some target atom, and they're firing a beam of neutrons at it, and hoping they stick. And then when you've got a certain number that stick, then you're like, did it? We got 108.
Well, and more than just getting the neutrons to stick, you also need them to undergo beta decay so that some of those neutrons now become protons, and now you have a heavier atom. So here you're replicating the conditions that you get inside of the atmospheres of stars and in some processes in supernovae that allow the heavier atoms to get built. A lot of these heavier atoms are unstable, they collapse quickly, so we don't even get to study their properties unless we are able to build them in one of these accelerators with a neutron beam.
Right. Okay. And so you mentioned the different kinds of flavors, right? So we've got the different kinds of experiments. You talked the neutron beams. You're making antiparticles for cancer treatment. What else are they doing?
So then you also have some of the ion accelerators that are smashing together heavier mass atoms and recreating the conditions inside of supernovae. So we hear all about CERN recreating the Big Bang. But then you have other laboratories like the National Superconducting Cyclotron Laboratory, which is the longest named of the labs, I think. It's up at Michigan State University, and they're smashing together ions and recreating the conditions in supernovae to see how is it that these different stellar nucleosynthesis events can take place.
And what is the difference between the linear and the circular ones? I mean, is it just
Well, if you think about
size,
it, it's size and also the potential energies involved. With a cyclotron, you can just keep ramping up the velocity by circling and circling and circling until you have the energy that you want in the particles. With the linear accelerator, you're kind of stuck with that one track. But linear accelerators were how we focused for a long time before people committed to building Fermi National Lab and the National Superconductor, and Brookhaven has a cyclotron. Harvard had one for a while. It started out that the really big accelerators were often linear accelerators, and cyclotrons were your university-sized facility. But once you started getting to, well, Fermi National Lab here in the United States, they disbanded a town to put the facility in. So where there used to be a town, there's now a large pair of circles that are filled with buffalo. And literally, Fermilab has buffalo.
Yep.
And then CERN's even bigger, and it spans both the Swiss and French countrysides. So once you need to reach the sorts of energies that are achieved by these giant facilities, it's hard enough to find area big enough to build the circle. Imagine trying to build something linear to do that level of acceleration. You're just not going to do it.
Do you remember the plans to build the superconducting super collider back in like the 80s and 90s?
Yeah,
and then that got
down
canceled?
in Texas.
Yeah.
Yeah, that was actually a very ugly situation, especially for the farmers involved, because they went down. It was in Waxahachie, Texas, and the government went down and used eminent domain to take away a lot of farmers' fields and paid them an amount that they claimed was fair market value, but none of the farmers could afford to buy land to replicate their farms, and they ended up having to find new careers. Built this huge facility that, had it been completed, would have revolutionized a lot of our understanding of particle physics. But at the point where they dug the giant hole, where they had all of the caves in place, where instruments were starting to get built at a variety of universities around the United States, there was a congressional blowback that this project had taken too long. Well, it turned out it was harder to build the holes than they'd thought. It turned out the equipment that they had to innovate from scratch wasn't as easy to innovate as they'd imagined. So there was congressional blowback, just like there's been with the James Webb Space Telescope and so many other major facilities. And so Congress decided to close down the facility. Partially built, fill in the hole, canceled all of the instrument plans, essentially fired all of the scientists, and then when they were done filling in the hole, they sold the land for a cost significantly higher than they bought it from the farmers, sold it off to developers. So now you have no science, no farming, and a bunch of developers making money.
Right.
And so that was a tragedy at every single turn.
How would it have compared to CERN, to the Large Hadron Collider?
Well, it was a completely different. it worked differently from the way they're working CERN with the Large Hadron Collider. This was one that was going to be looking at moving heavier mass objects. And so instead of doing the proton-electron, the colliding of hadrons that you see at LHC and with the prior instruments they had there, instead, it would have been, again, looking, from what I remember on this one, looking at colliding, again, the ions.
Right. So then, we've talked about how the structure and a bit about how they work. So what kinds of answers in science, and especially in our case, we're interested in astronomy, but what kinds of questions can we answer with these particle accelerators?
Well, depending on which one that you're looking at, it's how do I cure cancer, how do I replicate the insides of a supernova, how do I replicate the Big Bang? And my favorite is it possible to create a microscopic black hole in the laboratory? And I think the replicating the events in a supernova is in some ways both the most mundane and the most interesting. We often say in astronomy, we're made of stardust. That's probably the most common stated. It's on jewelry, it's on posters, it's on inspirational this, that, and the other thing. But it's a very easy thing to say, we're made of stardust. But let's prove it, and prove it in detail. And when we look at supernovae, we see the heavy atoms in the clouds of dust and material around them. But exactly how do you go from a normal composition star to all of these heavy atoms? Well, it's those intermediate steps that we've worked out on paper. Even graduate students are required to figure out many of these reactions. But how do we replicate it and make sure that our theories are right, make sure that our detailed understanding of particle physics is right? The awesome thing is for the most part, it is proving right. But then there's the open questions of, well, how did we end up in a universe that has more mass than antimatter? Where are the different asymmetries, the things that break down when we look at the details of particle physics? Well, it's when we make these collisions, when we start creating the antimatter, we're able to figure out, oh, so this is where this symmetry breaks down, this is where this symmetry breaks down. And it helps expose, well, what's under the hood of our universe.
Right. Well, so what would one of those experiments look like? Like if you're trying to replicate a supernova without an actual supernova, what would that experiment look like?
So you have several different processes that you're worried about with supernovae. With supernovae, one of the things that you get is a flood of neutrons that come pouring out. And when that happens, those neutrons bombard the centers of atoms, and as they build up, as they hit certain densities, you end up with a form of beta decay that ends up with some of the neutrons becoming protons, and they release energy and neutrinos and all sorts of stuff in the process, and you can quickly climb up through the atomic levels if you keep bombarding that system with neutrons, so that as it jumps from one unstable place to another unstable place, you can eventually land somewhere stable. There are amazing science maps that show this band of stability in the isotopes, and as you go up the center, it's a graph of number of protons, number of neutrons, and so you start down at 1, 1, and then you just build your way up, and you can follow this line of stability. And in a really good one of these isotopic maps, it will show you what are called the rapid process and the slow process, the R process and S process element formation paths that just show the various decay rates and growth rates that occur through beta decay and inverse beta decay.
And so you can try to replicate those different conditions and see if things pop out in the way that you're expecting.
Exactly. And it allows you to get an experimental hold on things like what is the half-life of this or that. Trying to understand how long something lasts for mathematics is not exactly, it's just easier to build the thing sometimes.
Now, one of the big mysteries that I know sort of we've been talking about, and it hasn't, it's only been partly solved since we even started the show, 7 years now, is dark matter. So how do particle accelerators help us with dark matter?
That one's less straightforward. So one of the things that they do is try and create neutrino beams with some of these accelerators. There's a facility down in Italy that has sent neutrino beams up towards experiments at CERN, not the collider experiments at CERN, but detectors at CERN, looking to see if they can measure the oscillation of neutrinos as they go from tau and muon and electron back and forth and so on, and their different flavors of neutrinoness. There's hopes that with dark energy, the
Dark
similar
matter?
types of you said dark energy,
Oh,
didn't
did
you?
I? I said dark matter.
Yes. Oh, I heard
It's okay.
dark energy.
Yeah.
I can answer that one far better. Sorry, Preston, you're going to have to cut this out. Can you ask your question again so I can answer the correct one?
Sure. And then do you want to do the dark energy one as well?
Yeah.
Okay, cool. All right.
Sorry,
So,
audience.
so one of the things that we've been dealing with since we started Astronomy Cast was this idea of dark matter, and it's still kind of a bit of a mystery. But I know particle accelerators have been brought into this search for dark matter.
And it's going to be interesting in the next few years as they try to push the Large Hadron Collider to higher and higher energies. There's supersymmetry theories that many, if not all of the particles we've discovered so far have a partner, a supersymmetric particle that's their partner. And these sister particles, some of them are projected to be what we now perceive or observe as dark matter, particles that don't really interact via the electromagnetic force, they don't stick together, but do quite politely interact via gravity, creating microlensing, creating acceleration of galaxies that are orbiting, of stars that are orbiting in galaxies. So we have to find these particles with these strange sets of interactions. And neutrinos have a lot of these characteristics, but they don't exist in high enough numbers to be all of the projected dark matter that we're seeing. So with particle accelerators, what they're hoping is as they push to higher and higher energies in that chaos of forming particles that comes out of that high density region of energy, some of the lowest mass dark matter particles, lowest mass supersymmetry particles, they're hoping they're the exact same thing, will get formed and we'll be able to go, aha, I got it in the laboratory. They're also using large basically the same detectors they use for neutrinos to look for dark matter. And it's hoped that they'll perhaps be able to find some of these as they look for the flickering interactions that indicate that one of these mysterious particles has had one of its extraordinarily rare interactions with one of the forms of heavy water or other fluids that they use in these neutrino detectors.
Right. So I guess you've got the two ways, right? The one option is you just have this big detector and just hope to find natural dark matter particles, or you generate them in the particle accelerator and then try to see if you're catching them. So we talked about dark matter. What about dark energy? Are there ways that we can use particle accelerators to find dark energy?
That one starts to get much more challenging. We're still trying to figure this out. We're still trying to understand what the heck is dark energy. And part of getting at it is understanding better how it is that particles form, how they change. One of the experiments that's getting done is there's a lab in Italy that's generating a neutrino beam that they're shooting up towards one of the instruments at CERN, and they're looking to try and measure how do the flavors of neutrinos change over time. How do they go back and forth between muon, tau, and electron flavors or of neutrinoness? There's similar experiments in North America. And as we try and understand more and more about these different types of interactions, theorists are working to try and understand how is it that, well, we know that energy is constantly turning into virtual particles, and those virtual particles are turning back again into energy. And one of the thoughts for dark energy is maybe somewhere in this there's energy released that everything isn't properly conserved, and people are trying to to understand all of these pieces through accelerators. They are also building telescopes where they're trying to look at what's happening in the earliest moments of the universe. It's a completely different discussion.
Yeah.
So we're doing everything from trying harder to understand particle physics to trying harder to understand the formation of our universe, where we're going to find the answer to dark energy. I don't think there's even a gambler willing to pick up that bet.
Right. I love this idea that you just take your neutron beam and you just aim it in the general direction of CERN, and it goes right through the Earth and reaches the detector. You don't need to build a tube or anything because the neutrinos just don't even care.
And nuclear power plants, you can tell whether they're on or offline by the neutrinos you're receiving.
Right. So the last thing I think is really interesting. Well, we talked about. Well, there's two that I want to talk about. I'm running out of time, but one is creating these black holes, which you mentioned briefly. Like,
yes.
Whoa, well, how does that work?
Yeah. Well, so what is a black hole? It's extraordinarily dense mass. It doesn't matter that you have a lot of mass. What matters is the density of the mass. Can you stand on the surface of that mass and have to go greater than the speed of light to escape the gravitational pull of that mass? And so it's theoretically possible to create microscopic sized black holes by just slamming things together with a beam that is tight enough and an energy density that's high enough that, well, you meet those criteria for forming a black hole. Now, if you're able to do this, one of two things is going to happen. That sucker is either going to just quite haphazardly sink down to the center of the gravitational well that is the planet Earth. It will oscillate for a while as it works to get there. Happily passing through the bulk of all of the atoms on the planet, it will maybe eat, like, I ran the numbers a few years ago, and it was just a negligible number of atoms such that a couple grams will be eaten before the sun starts to destroy our planet. So this is not a concern if this happens.
Yeah.
But the more interesting thing that could happen is it could evaporate. Its event horizon would be so small that it's evaporating faster than it can consume energy from normal conditions. And if that microscopic black hole is able to evaporate in the flash of light that's predicted, then Stephen Hawking finally gets his Nobel Prize, which I think would make a lot of people happy.
And so the last thing before we go is replicating the conditions of the Big Bang, which is crazy.
Yes. Yeah. So I mean, if you think about it, what was the condition of the Big Bang? It was dense. And so all that it takes to create to start to replicate the conditions of the Big Bang, you have to take energy and compact it into the densities that were experienced at different points after a universe had started to expand out. And supernovae are pretty dense, but the early universe was even more dense, and that just requires higher energies and tighter focus.
So you're just smashing the particles, and they're piling up in a pile in the middle of the accelerator, I guess the experiment.
No pile, they're turning into energy in the center.
In the center, and the density of that area gets higher and higher and higher until you're starting to replicate. And I know I was doing a little research on this, that in the LHC they got into the trillions of degrees for one of their experiments.
And what I love is, as you start talking about particle physics, when they discuss the mass of things, they stop using normal units and start discussing the amount of energy that's contained in something instead. Because when you're dealing with relativity all the time, it's just easier to work in units of energy. So here, normal energies are in the giga-electron volts, and you just work your way up from there. Tera-electron volts is now not too uncommon for these giant research colliders.
What will be next? Electron volts, yeah. It's crazy. Cool. Well, thank you very much, Pamela. That was awesome, and it's great to have you back.
It's good to have you back as well. We both took turns not being here this time.
All right. We'll see you later.
Okay, see you later. And now I have to use my sideways monitor again.
Okay, cool. So we're just going to stop. We're going to save our files and make sure that all worked, and then we will start answering some questions.
Okay. I wish I had the brain power to figure this out without turning my head sideways, but I don't.
Can you turn your monitor sideways? How about you just don't
No.
even look and I will just read the questions out to you?
No, I'm good.
Okay.
No, I'm not.
Okay. Okay, so questions. Let's see. I wonder if I can pull these questions into the comment thing, because there's a really cool way that I can highlight them. I can only highlight the YouTube ones, I think. Let me see if this works. Okay, yeah, so this will work. Okay. Hold on. I apologize.
The tutorial video makes it look so easy.
It's so easy to do this now. Right, so someone asked, and I apologize, and I'll dig up the name as I ask the question. How do they get single things? So, this idea of like taking a single
Filtering.
proton or single electron and then firing that down the accelerator so that it smashes into something. What is that? I mean, how do you get one atom of a thing?
So it's different forms of filtering. You have your magnetic field set in different ways so that if something doesn't have the precise exact velocity, it ends up getting bent into a completely different direction. And so in the end, you end up with only the electrons that have the exact precise velocity you want. And if you start with a low enough power, you end up with essentially one electron. Now the reality is they are generally dealing with a beam of electrons, a beam of protons, but they use filtering to get it down to exactly what they want. Just like filtering the sun, just different, use magnetic fields.
But the fact that they know that they've got just one particle, but they're often like firing streams of them in a calculated way. They're not just like plucking out like with their little magnetic tweezers, grabbing one particle, and that's the one they're working with today.
You can get it to one electron, especially if you're doing research on interferometry. You want to be able to do things like that, and it's the type of thing that is annoying but not that difficult to do. You take an atom, you excite it to the ionization level of the electron. Electron pops up. You now have an electron. Happy electron.
Okay, so M. by Shival asks, now that the Higgs boson has been found, do you think that we'll find any other new things in the near future?
It depends on if supersymmetry is right or not. If supersymmetry is correct, then we are nearing being able to start revealing a whole new family of particles, things that currently only exist in diagrams and books as possible things. If we do find those, Steven Weinberg gets another Nobel Prize. We're starting to hit the age of Nobel Prizes in particle physics if we keep finding things.
We did a show on supersymmetry. Has your thinking changed on that matter since we did that show?
I still am kind of dubious about it, but it's the only reason to keep firing these things. So let's keep looking until we disprove the theory. It's completely fine for me in an absolute lack of evidence to say I'm not sure supersymmetry is necessary for the universe. But that's a personal opinion, not based on facts. It is not reason to shut down amazing research facilities that will observationally say with data whether supersymmetry exists or not. So we need to look, even if my gut says, yeah, probably not.
So here's a question.
Science.
Right. Here's a question from YouTube. Check this out. I can make this go. So how close to the speed of light are we going to be accelerating these particles? We actually didn't mention that in the show. How fast are they going?
It depends on the mass of the particle. So the issue is the heavier the particle starts out, the more energy is required to get it going faster and faster and faster. So at a certain point, you start hitting the limits of how much energy you can inject into the particle. So for the lightest weight stuff, you start going at, I want to say you start getting close to 90% the speed of light, but that is memory speaking.
Well, here, hold on.
Uh,
Jose Gonzalez has given some numbers here. I'll put that up.
okay.
So they acquired 99.9% of the speed of light, and it takes 90 microseconds to travel one revolution around the LHC.
Okay. Okay, so that's with LHC.
Yeah.
As when they're accelerating instead ions that are much more massive, you're not going to get anywhere near that fast.
Check this out. Will-eyed Oni says the Higgs bison at the Fermilab. So remember you mentioned the bison there?
Yes, I think we do need to call them that.
The Higgs bison.
What's so frustrating is it now looks like had they just pushed Fermi to go to some higher energies, they might have been able to get the Higgs boson at Fermi first, because there is not significant enough data from the last experiments they did with Tevatron. So it could have been the Higgs boson.
Andrew Planet, our good friend Andrew Planet asks, is a black hole high energy jet like a particle accelerator? And I mentioned natural and unnatural, or natural and man-made.
Right.
But we didn't go into some of the natural ones. But yeah, it is, right?
So it's sort of. It's not that the jet is the particle accelerator, it's that it's the accelerated particles. So you have, with a black hole in many cases, a disk of material surrounding it, an accretion disk. And that disk of material is extremely hot, so it becomes charged particles. Moving charged particles create a magnetic field. So in this case, you have a circling disk of charged particles. In the case of an accelerator, you have electrons in electricity quite often in the most simplistic accelerators, like lab bench simple cyclotron, generating a magnetic field. So just like that disk of electrons in your very simplistic cyclotron can generate a magnetic field that accelerates particles inside the cyclotron, in a accretion disk, you have a disk instead of a donut of circling electrons that generate jets coming out either end instead of a donut of particles going in a circle.
Tom Nath, our other good friend Tom Nath, you have to tell me, Tom, how to describe it. What happens to the excess unused particles? So, you fire up this big beam and you fill it with particles and you're firing them down towards the target, and then are there leftover particles both in the creation point or just that they have
what
to deal with? What
happens to the aftermath?
Yeah, do they have to decelerate them? What do they do? Do they all just disappear?
So they fire together a pulse of particles. It's not like they fill the entire cyclotron with a solid beam that wraps all the way around. They'll have a spatially separated out pulse of particles, a little stream, not a whole thing filled with stream. And that way they actually only have to turn on the magnets in the area of the accelerator that the particles are in. And so this small beam, not giant streaming beam, but this small segment of particles, all of it goes into the detector. Now they do have holding rings. So if you look at aerial photos of CERN, Fermilab, they're double rings. And they can use one ring as a holding zone at a lower velocity and then inject it into the bigger ring to get to the final velocity and then slam into the detector.
Oh, that's really
Once the slamming goes on inside of the detector, with some of the detectors, they're surrounded with photomultiplier tubes to detect the particles coming off. In other cases, they have webs of fiber optics that are capable of trapping the particles as they flow through. There's a myriad of different ways to detect all the different energy things that come flying out, so that you can track what is the mass and energy of what went this way, what is the mass and energy of what went that way, what are the velocities, and it's by figuring out essentially what are the momentums of each of the different particles that they're able to piece together what was it that the particles were.
So it's kind of like when you think about when archaeologists are dealing with a dig, and you're like, "What do you do with all the excess stuff?" Well, there is no excess stuff. They are interested in every single bone fragment, piece of chip pottery and paint fleck
Yeah.
that they find, because it's all used to get to the bottom of this mystery. Um,
And everything that gets created for the most part is unstable and self-annihilates very quickly as nothing more than energy that's flowing
right.
away into the
Just
rest of the
cleans
universe.
up after itself. You don't have to worry about it.
Yes, it does. Occasionally
Mary
it destroys things.
Mary Bradley asks, what is the difference between an accelerator and a cyclotron?
Um, a cyclotron is a kind of accelerator.
And it's the
So we
circular kind.
talk, yeah, so we have synchrotron, a word I can't say, which is why I avoided it in the show. Synchrotron accelerators and cyclotron accelerators, and they simply use magnetic fields in a different way to accelerate the particles, but they're both types of accelerators.
Right. So someone says, we've got a cyclotron here at the hospital. That means they've got a circular accelerator.
Yes.
Okay. Um, William Keller says that this one made my brain ache. Sorry, William.
Hopefully it ached in a good way.
So Hugo Burnham brought in some additional information that the community of Weston voted to disband itself as part of
Yes,
getting
that's
the
true.
Fermi Lab in. And so you use the word disband, which sounds like that's like something quite sort of evil done to the town, but actually they...
Yeah, but the town council did it to the people who live in the town.
Yeah, so at some point somebody was probably not happy with having their town taken apart for a particle accelerator, but they voted on it.
Yes.
Um, let's see. Thomas Traniker. Well, this is sort of a conversation, but I guess the gist is: do you make the particles radioactive when you accelerate them? Where does the radiation come from?
Well, radiation is a tricky word because many different things get referred to as radiation. So, for instance, when people start talking about alpha particles, that's just a helium atom that's moving really darn fast with special characteristics. We don't normally think of helium as being radioactive, but if you strip it and you fling it hard enough, it gets destructive when it hits things. Gamma rays are talked about as being a form of radiation, but those are just photons of light that have an extraordinarily high energy. We also talk about atoms that are unstable and undergo forms of either beta decay or inverse beta decay, which leads to neutrinos and high energy particles being given off as being radioactive. We talk about beta particles. All of these different things that we worry about, those are just neutrons. The reason they get called radiation is because of how they interact with the world around them, how they generate X-rays, how they blast things apart, how they destroy DNA, because these are energetic things that break molecules apart, and we're made of molecules. So when we talk about accelerators, when you're replicating the insides of a supernova to create heavier and heavier atoms that aren't stable, those are radioactive particles. But when you talk about an electron with an extremely high velocity, whether or not you want to call that radioactive, I think depends on if you're worried about shooting it at somebody's DNA. Definitely, if you shot that electron at somebody, it would blast their DNA apart. That's a bad thing. But it starts to get tricky. Some words aren't as precise as you'd want. That's one of them.
Right. So a couple more questions here. We'll do one more here. Sophie Molzen asks, can you make gold atoms in a particle accelerator?
Yes, alchemy is real and true. The
Gold.
amount of energy, the cost of the amount of energy makes this not a process you want to do, considering you'd be building it an atom at a time and probably overshooting and making other things periodically. Yeah, don't do it. It's possible, but don't go there.
But you know, for example, if we want to make antimatter as for our future spaceship, that might be the way it's going to happen, is building it up one atom at a time, one
And this is
antiparticle at a
why
time.
interstellar travel is energy prohibitive. I mean, as it is, we're almost out of the nuclear materials. The I believe it's plutonium that gets used in radiothermal generators, like the one that's on Mars Curiosity.
Yeah.
And that's all material that's built up inside of accelerators.
So Hudson Ansley asks, what do you think about the recently demonstrated electron accelerator on a chip? I haven't heard about that. Have you heard about that?
No, I
Don't
haven't.
electrons move at the speed of light? Anyway, we'll have to look into
No.
this.
No, electrons do not move at the speed of light. Photons move at the speed of light.
Yeah.
Electrons have mass.
Right.
Electrons have
Okay.
mass, therefore they can't go that fast.
Electricity moves at the speed of light, and electricity is transferred by electrons. Anyway, well, I think we're good. There's a couple more questions here. But definitely check out the comments over on YouTube, because Jose Gonzalez has been answering questions, just everyone's questions. It's fantastic. So he
That's
clearly
awesome.
knows his particle acceleration information physics. So it's great to see some questions there. So cool. Okay, well let's wrap this up. So again, great show, Pamela. Thank you very much, and
Thank you.
we'll see everybody. And thanks everyone for watching, and we'll see you all next week. What's the next thing that's happening on the various shows?
We
Learning
have
Space?
Learning Space on Wednesday. I think Learning Space on Wednesday, and then the weekly Space Hangout on Friday.
Sweet. Okay, and what time does it start on Wednesday?
It starts at 6 p.m. Central, 4 p.m. Pacific, 7 Eastern, midnight London.
Any topic? Do you know what the topic is this week?
No, I have to admit I don't.
Okay, no problem. I know
It's Nicole Gallucci's baby.
Yeah. Okay, cool. All right, well, thanks again, and we'll see everyone next week.
Sounds good. Bye-bye. Amazing geology and biology, because it's an island that's very, very, very young and not yet tamed. So that was kind of cool.
Wow, I'd love to get there sometime. In fact, we had an astronomer last night in the virtual star party from New Zealand. I don't know if you met him, Astro Stu, Paul Stewart, and he was broadcasting the sun live into the star party while we were doing the night stuff, and it was just the most amazing video, just unbelievable.
Yeah. New Zealand is 2 different islands, and they refer to Australia as the West Island. And I was up on the North Island, and Paul lives down on the South Island.
Okay, so if people have never done this before, if you just want a reminder, what we're going to do is we're going to record our episode of Astronomy Cast live. So we're going to, you get to watch as this stuff just tumbles out of our brains, especially Pamela's mighty intellect. I'll ask a bunch of questions, she'll answer them, and that will be our episode. And today we're going to do a show on particle accelerators, which is great. I'm really excited about this. Pamela's like, oh, why don't we do particle accelerators? And I'm like, yeah, let's totally do that. Some episodes I'm super excited about, and this is one of them.
Well, there's a lot of misinformation about particle accelerators, so it seemed like a good thing to do.
Like what they are. Is the start. The other thing is, right, and so then now you can interact with us. So we're going to record the show. It takes us about 30 minutes, and this is the show that normally goes out into the podcast feed and people consume. But we actually stick around for another 20 minutes, half hour after that, and just answer your questions about space and astronomy. So there's 2 safe places that you can ask your questions now, and unfortunately, the technology that we use to keep track of all of the information is not as available to us anymore. So the 2 places to look, the 2 places that I'm going to monitor are on the event page. So if you're watching that on Google+, there's an event page, and if you're watching it there, I will be able to catch your question. I can see Graham is making comments, Paul Steele, Kevin Parker. So that's the place that you can make some questions. The other place is over on YouTube, and I'll keep track of the comments on YouTube as well. So if you're watching it anywhere else, literally, if you're watching it embedded on Universe Today or over on CosmoQuest or anywhere, you're going to want to click to watch it on YouTube or find the event page on Astronomy Cast's Google Plus page. Those are the two places. I can't guarantee I will see any other questions or comments. So, yeah. So and feel free as we record the show to jump in and fix our mistakes, and I will try to catch them and we'll incorporate them into the show. Or if you have just questions that have nothing to do with what we talk about today, we're glad to deal with those after the show. And you can experience the vast, sweeping intellect of Dr. Pamela Gay.
I can't hear you say that without giggling.
The vast, sweeping, mind-bending intellect of Dr. Pamela Gay. All right. Okay, now let's just set this up to record. You ready?
Yeah. Hold on. This is where I have to like figure out how to move my mouse on the screen that's rotated. Ah.
So your monitor is rotated, right? So you're actually that is some technology.
Stop laughing at me.
That's awesome. That is a new form of technological fail. I've never had it's stuck on, like, you just turn your monitor sideways, prop it up, hold it out sideways.
Pretty much. Stop.
Make sure it's on mono.
Yeah, it is. It is. I'll be back to normal in a moment. Okay, I'm ready to press record at any moment.
Is it on mono?
Yes.
Cool. All right. And now I'm not pretty. Hold on. Sorry. We always explain that this is the sausage factory thing. Okay, cool. And I can see the people over on YouTube as well. Okay, good. I'm ready to go. I still know how to do all this. Are you
And
the
you don't.
technic? I was going to wonder if the technical gremlins all worked out.
I still have one monitor that is displaying everything rotated at a right angle.
And I see your face being sort of delayed in strange ways. So, so I think we've got enough of the technical gremlins worked out that we can proceed with the recording, and we'll see how we go from there. Well, hey Pamela, it's good to
Yeah.
see you again.
It's good to see you. How are you doing?
Good. Did you have a good summer?
I had a long summer.
Yeah, we had a really great warm summer. We swam in all the places and jumped off all the things into the water, and that was literally all we did every day. We just went swimming,
Oh,
jumped
wow.
off things, rinse, repeat. Sometimes twice or three times in a day. It was great. Yeah. But you,
I
but the
jumped off nothing into water.
well, it's not as fun, I think, to jump into lakes and oceans. But you had a really cool trip. You did a trip to New Zealand.
Yes, that doesn't count as summer anymore.
It's
That
it's
was
winter.
recently. It's definitely fall, and getting down there, it was definitely the end of their winter going into spring. All the tulips were in bloom. Yeah, I went down and went to Wellington, Melbourne, and Sydney and gave about 2 talks a day for a week, and it was an insane whirlwind trip. And Wellington has the most